All right, so to do this, to be able to answer this question about what the most efficient way is, we first need some tools. So it's kind of like you go out, you're going to build a new shed in your backyard, and you realize, oh, I got to go down to Home Depot and buy me a new saw or a new hammer or a new whatever to do this new drill to do this job. That's kind of what we're doing here in math. If we want to be able to answer this question on what's the best way to visit a bunch of cities, the cheapest way, most efficient, effective way, costing us the least time and money, then we need some tools to help us answer this question, some mathematical tools. And the first one, the main one, is we need these circuit graph things. This 6.1 will be very, very easy. It's just basically getting comfortable with these circuit graphs. Let's talk about something called a Hamilton circuit. What is a Hamilton circuit? Hamilton's the math person that came up with a bunch of this. Hamilton circuit visits or touches each city only one time. In other words, you don't want to repeat, right? If you're trying to do this in the most efficient way possible, you don't want any repeating. You don't want to go to the same city twice. So we're looking at this, we're saying, okay, what's a way to cruise around and hit every point only once? Now, let's look at map A first. Look at map A. So this is like, pretend A, B, C, D, E, F are 6 cities, and you need to deliver whatever, FedEx needs to deliver goods to all those cities. They're saying find all possible Hamilton circuits. Notice, how could the planes, the FedEx planes, fly if these are the only routes? In other words, you can't fly straight from A to E because there's no blue line there. Does that make sense? The blue lines are the allowable, possible flight routes. So you can fly straight from A to B. Whoops. You can fly from city A to city B. There's a route. But you can't fly straight from A to C. You have to go through B first. You can't fly from A straight to D. You can't fly from A to E. You can fly from A to F, though. And on you go. So is that making sense, what we're looking at? So these graphs will represent possible roads between, roads if it's on the ground or flights if it's in the air, ways of connecting cities to cities. All right, so if that's the case, if those are the only possible connection routes, what's a Hamilton circuit, meaning what's a way of visiting, whoops, I didn't mean to erase that, visiting all the cities? Well, I've already answered the question for you right here, you can say. It is starting at A. Let me do the right one, then I'll go back to the wrong one. This means this A, B, C, D, E, F, A thing. This means go from A to B to C to D to E to F to A. Which, yeah, that's obvious. Just go around the horn. Just go around the outside. And then it gives one more. So there's one other way of making a loop. Starting, if the plane starts in city A, goes A to B to E. I'm just following this route right here. A to B to E. Where do you go next? D. Tracking with me? And then C. And then F. And then back to A. And we hit every city only one time. So that's another, what we call Hamilton circuit. What would, maybe it'd be helpful if I said what would not be a Hamilton circuit. What would not be a Hamilton circuit? Say you said, okay, I'm going to go from A to B to E to D, C, back to E, F, A. That would be bad. That would not be a Hamilton circuit. Why? What did I do wrong? Did you see I hit E twice? Maybe I should see what that letter is now. Let me show you that again. So remember, you can't hit any city twice because that's just not efficient. You're just wasting time and money if your trip hits the same city twice. So again, if I went A to B to E, D, C, back to E, see that? That would not be a Hamilton circuit. Hamilton only hits every city once. It's just saying that's not a good plan. It's not a Hamilton. Hamilton said, but basically it was a math guy that said the deeply intelligent statement that you should only hit every city once. Well, of course, only hit every city once. So a Hamilton circuit Only one time. Hits every city only one time. Okay. So what are all the possible Hamilton circuits? Well, you can see answer A is not right because it says go A, B, C, D. I'm just doing it, showing why this is not right. E, F, A. What's wrong with that? Well, that's not the only one. The other one, that is one of them, but the other one is this one here. So you see why the answer is not part A? What about part B? Is it part B? A, B, C, E, F, D, A? Why is that not right? A, B, C, E, F, D. You can't go from F to D, can you? See, this is bogus right here. See how it says you go from F to D? They're making stuff up. There is no direct flight from F to D, at least in this map, right? So that's why B, A is not the right answer, B is not the right answer, and D down here just has, oh, it goes F to D again. Yeah, see how it's going F to D right here? You can't go F to D. There's no direct flight from F to D. It doesn't exist. See, there's no connection from F straight to D. It doesn't exist on the map. So that's why answer D is also wrong. So the answer is C, the two routes I showed you. What does it mean by and their mirror images? Do you get what it's saying? It means you could run the loop backwards, right? In other words, you don't have to say, I'll just repeat what they said. They said A, B, C, D, E, F, back to A, right? A, B, C, D, E, F, back to A, and then that other one also. But you could run that backwards. You could go A, F, E, D, C, B, A. I'll just write it that way. A, F, E, D, C, B, A. That's the same loop, isn't it? That's the mirror. That's the mirror image. That's the same loop backwards. You just go A, F, E, D, C, B, A. So of course, so we always say, yeah, of course, any loop could be run both ways. So that's all they're saying when they say, let me get rid of all this scribbling here. When they say the answers are this loop and that loop and their mirror images, meaning those two backwards. Same loop. Is that good for the first one? We're just saying what's a loop? Circuit just means a loop. What's a loop? That hits all the cities exactly one time. Well, there's two possible loops. So if you were the manager of the FedEx group that was supposed to fly to all those cities and deliver packages, you would basically look at these two different loops and decide which one's cheaper, because those are the only two loops that are going to hit all the cities. So you would just add up the cost of going this way and add up all the costs of making all those trips, and whichever one was cheaper, you'd have the company go with that particular loop. So that's the deal. We're trying to say, okay, what are all the different ways that we can accomplish this? And then in a minute, we'll start putting numbers on them, and the cost of the various flights, and we'll add them up and go with the cheapest one. Make sense what we're doing? So this first section will be really easy. It'll just be fooling around with graphs and counting things. Let's look at part B. So part B is this one over here, for part B down here. They say choose the correct answer. So how many routes are there on B? On B, there's really just the one around the outside, huh? A, B, C, D, E, A. There's no other way to make a Hamilton loop or a Hamilton circle other than just going around the outside for B. There's no other way to do it. Do you see that? Anytime you go inside, like let me try one. Anytime you say, well, I'm going to go A to D first, you're going to get messed up. There's going to be no way to hit all the points without repeating a city. And you don't want to repeat a city. That's wasteful. Right? Think, what are you going to do? D to C. Now, if you go back up here to A, then you're going to hit A again. That's not allowed. So you got to go to B. And now what? You got to go back to A. And you haven't even hit E yet. So you're wasting. It's not there. So there's no other way. There's no other route. There's only the outside is the only Hamilton loop. The only loop hitting every city exactly once. So that's why that's the answer. And it's mirror image, meaning go the other way. What's wrong with the other answers? Well, they must make up routes that aren't even there. Let's see. How about this one? AC. Can you go directly from A to C? Yeah, you can, huh? AC. That's possible. To D. Yeah, that looks good. Anybody see any problems with this one? to E, and then B. Oh, right there. No, there's no E to B route. They're making stuff up there. Yeah, right there. That E to B is bogus. That's not legitimate path. There's not a flight from E to B. So, all right. So for those kind of reasons, you can look through these. Those other ones are wrong. The answer is just the A. Good on that. All right. I'll keep moving. Okay. Begins at A and ends at F. So if you start at A here, and you're going to go through the loop and end at F, well, they're telling me this. We've already got the right answer here. Let's see why the other ones are not right. Like, why is this not right? That's the answer I guessed at. You can see I was going through the homework quick and it marked me wrong. So that's what I guessed at first. So A to D to G. Oh, right there. You can't go D. Can you guys see it? Is it too small? You can't go D to G. So that's just craziness right there. You can't go D to G. So that they're making stuff up again, right? There is no D to G path. So that's not right. And then for similar reasons, the other ones are wrong. Good? Good enough? I think this will be easy for you. Hamilton just hits every city only once. All right. So I'm going to, if you're okay with that, I'm going to. Okay. So they're saying, so do some Hamilton things. Start at, see how they're all starting at B? All the answers start at B. So just want me to take that loop and start at B. And so the rest is the same. So the answer is this B, C, D. So B, C, D, E, A, back to B. What's wrong with the other answers? They must have a bogus connection. Let's see. B, C, E. Can you do that? Oops. B, C, E. B, C, E. Yeah, that's okay. D, A. D, oh, no, you can't go D to A. See, that's made up right there. All right, you got it. They're making up roads that don't exist. You can't go, there's no direct flight from D to A. Can't do it. So that's why B, and I'm sure there's some other reason like that why C is no good. So it's only A, so I'm going to move on. You guys okay with that? These are just spend time looking at the graphs and finding which ones are allowable or not allowable. I think it'll be easy for you. Okay, so here they're saying now these are weighted graphs, which means they're telling us how much each flight costs, for example. It could be all kinds. We don't know what those numbers mean. It could be the distance in miles, could be the cost of a flight in thousands of dollars, could be what it costs the company to fly their plane from, it's whatever cost. Could be time, how much they got to pay their employees to get the pilot to fly from wherever to wherever, whatever. It's the cost to the company of the various roads and trips up there. So, okay, so here we go. So like that 10, for example, that means if you fly from E to A, it's going to cost you 10,000, we could say. It'll cost the FedEx company $10,000 to fly one of their planes from E to A, and on you go. Because not all cities are going to cost the same amount. It's going to be different amounts. So you see the different numbers for the different flights. Some cost more than others. So we want to say, okay, how can FedEx deliver goods to A, B, C, D, and E in the cheapest way possible? How can we use math to help them do that? Well, first off, they're going to say, question A, find the weight of edge DE. So DE is 6, right? I already answered that on there. DE is 6. And then next question, what is a Hamilton circuit that starts with DE? Well, DEB, I guess again we've already got the answers on all these. DEB A, where's A? Oh, it's up there. A, C, D. Yeah, so that's a Hamilton circuit, huh? Made the loop, hit every city only once. That's what the Hamilton thing means, right? Hit every city only once. That is a Hamilton. I don't know if that's the best one, but that is a Hamilton circuit. What's wrong with the other answers? Like, what's wrong with this right here? Must be, again, a bogus connection. No, but these have all connected, don't they? By the way, do you notice every city connects to every city here? So, which is more like real life. Mostly, huh? Mostly you can get a flight from any city to any city. At least in most industrialized countries. right? You get a flight from any city to any city. But they don't all cost the same. So this is more like real life. What we call this is a complete graph. Let me write that. It's a complete graph. And by complete, that's a G there. By complete, we mean all cities connect to all cities. You can get from any city to any city directly. There's a direct flight from any city to any city, which is more typical in industrialized countries. So, but they don't cost the same. They have different costs, the different flights. So we still have the issue of trying to do this in the cheapest way possible. All right, so let's get down here and look at this ED thing. Why does this not work? Start at E, bless you. Go to D, and then go to B next. This looks good so far. What's the problem? Go to A, looks good. Go to C, looks good. Go back to D. Oh, it didn't make a loop. We never got back to E. Did everybody see the problem with that one? Let me do it again. Yeah, that one's a little more tricky. Do you guys see what the problem was on that one? So let me track it again. Why is C not the answer? It starts out good. E to D to B. To B next, right? To B. E to D to B. To B. To A. To A. To C. To C. To D. To D. Well, you see how we never made it back home? There's home. There's where we started. You have to make it. It's a circuit. It's a circuit. It's a loop. You got to get back home. You got to bring the plane back home. So that's not a circuit. It's not a loop. It never returns. So notice you've got to have the starting and the ending letters be the same, don't you? When you're making a loop, you got to start and end in the same spot. Good? So that's why C is a bad answer, and I'm sure there's other reasons why the other ones are too. Well, actually, I'm kind of interested now. Let me see. What's wrong with this one? D, because this one starts and ends with D. So what is his problem then? D to C to A. D. Oh, wait, it's supposed to start. Oh, start with. They said they want you to start with DE. That one starts with DC, so they're being kind of tricky. All right, that's why that one's bad. Okay, now how about this one? This one starts with DE, and it has D on, starts and ends at D, so that looks good. What's his problem? DE. You already see what the problem is?
It doesn't have C.
Oh, good. Yeah, look at that. There's no C. There's no C, and it hits E twice, doesn't it? Yeah, so that's why he's bad. Yeah, so you guys can probably do this quicker than me. Yeah, so there's some kind of problem with all the other ones, right? They don't hit every city once. They don't start with DE like they said you're supposed to. And they got to make a loop. They got to start and end at D. All right, and what is the weight of this graph? Now let's answer this question. What is the weight of that Hamilton circuit? That means the total cost of all the trips. So let's put it back on the map. It's D to E to B. So D to E, so D to E to B, to A to C, to A to C, to D. Back to D. All right, so it's 6. Is that a 5? 6, 5, 9. Just adding up the costs here. 3 and 4, and you're back home. Is that it? 1, 2, 3. I think that's it. 7, 16, 22, 27. Yep, that was the answer. 27. So the total cost, like $27,000 or whatever, for FedEx to fly the plane between all those cities, to pay the pilot, pay the plane costs, deliver all the goods in that circuit, $27,000 cost to FedEx. Does that make sense? The total weight of that trip, the weight of that circuit. We call it weight, but it could be any kind of cost. And then on they go. What's a Hamilton circuit that ends with ED? And, you answer all the questions. Same kind of thing. So I'm not going to go through that. It's the same thing. Are we good with that? No questions? I'll keep moving. Okay. So first one here. I've already given you answers. So 6 with that exclamation point. What does that mean? That means 6, right? When you're really excited about it. How many pies are going to be there for Thanksgiving? 6! We have a lot of pies when we get the family together. Anyway, yeah, it's factorial. You're right. You're totally right. Johnny, you've got the right thing. It's called factorial. And what does it mean? Like, how do I get 720? What are you supposed to do? You guys seen it before? You start at 6 and you just multiply all the way down to 1. That's all it means. It just means 6 times 5 times 4 times 3 times 2 times 1. And that is 720, as the answer says. Now, you have a button on your calculator that'll do it automatically. At least most calculators do. So I'm glad to or you can just do it by hand. I mean, 6 factorial is not that big. It's probably quicker just to do it by hand. But like if they give you, and 8 factorial is not big either, but sometimes they will give you like 25 factorial. It might be nice to have that button. So there's supposed to be an exclamation, but yours, it would be, so if anybody has the TI, everybody has a different calculator. So, there's a couple of those, 3 of them. All right, I'll handle 3 birds with 1 stone here. So if you put the 6 on your screen first, hit 6. Got a clear screen, got 6 on there. Hit the P, I think it's the PRB button. See the upper left corner? PRB, stands for probability. And then go over to the right with the right arrow 2 times, see the exclamation point? Hit enter, it'll put it on the screen, and enter 1 more time, and it'll compute it. So 6. Yeah, go over twice. Yeah, so I'd be glad to help you after class. I'd be calculating. Oh, you have one too. Did you catch that?
Yeah.
Good. There were 4 of you I got with her. And okay, and you got one too? Yeah, same one. You guys get it? Hey, great. There was a lot of people that had that calculator. Good. Anyway, if you have a different one, glad to help you. Come up after class. They're all a little different, but pretty much find that exclamation point. So this one, same thing. You could just do these by hand. A factorial 8, 7, 6, 5, 4, 3, 2, 1, 40,000, 320. Notice these numbers get big fast, don't they? Right? 6 factorial is 700. It's under 1,000. And then you go up 2 more steps, you're at 40,000. Feel the weight of that, because we're about to find something about it. They get big fast, don't they? They get really big fast. Okay, now they're going to say, how many Hamilton circuits in K7? Now, what's K7? K7 means a complete graph with 7 cities or points, however you want to say it. I don't know why we use K, because the word complete has a C. I don't know, maybe some math teachers that were struggling with spelling. I have no idea. But for whatever reason, we use K. And now, what is complete? I said it a few minutes ago, but I know I'm talking fast and saying a lot of things. Complete means every city hits every city. There's a direct, every city directly connects to every city, which is usually the case in industrialized countries, right? So that's what a complete graph is. There's no roads missing. Every dot connects to all the other dots. So it's complete. There's no roads missing at all. You can fly from any city to any city directly. So if you have a complete graph with 7 cities, so that means like you got, see if I can come up here and draw it up here. If you've got like city A, and city B, and city C, and city D, it's a 4. City E, 5. City F, 6. And city G, 7. So that's 7 different cities. A, B, C, D, E, F, G, right? 1, 2, 3, 4, 5, 6, 7. Yeah, 7 different cities. How many different total connections are there going to be? Like you can, let me, well, the answer is going to be 720. It says it right there. How did they come up with that? How did they come up with 720? Do you know what the heartbeat of math is? What is math all about? Repetition. Well, that's true. That is actually true. That's true. And another fact is true. Math in the end is patterns. What math does for you? Because probably I assume most of you aren't going to work for FedEx and do this kind of thing. You're not going to literally do this stuff, right? Well, then what's the purpose of it? Purpose really, math as patterns, is to help you to deal better and better and better in your life with patterns. That's what math is. Math is the science of patterns. It's seeing patterns, predicting patterns, describing patterns, everything pattern. And who does that? Well, most people do that in their job one way or the other. What does a doctor do? He or she looks for patterns in a person's body, right? what are symptoms? There are patterns, right? What does a lawyer do? He looks for patterns. He or she looks for patterns in the law. And on you go. Pattern thinking is part of a lot of what we do. So what do I mean pattern here? What am I talking about pattern? Well, let me show you how to answer this question in a way that it'll make sense for all of you. So from city A, let's start with city A. We're supposed to connect to all the other cities. Remember, there's 7 cities. Let me just put numbers on. That'll probably help. This is city 1, 2, 3, city 4, city 5, city 6, and city 7. 7 cities. So starting from city 1, I'm going to connect to all the other cities. How many connections? I'll leave 1, 2, 3, 4, 5, 6. There we go. I connected A. I got more to do than that. Then I got to connect B to everybody and all the rest. But so far, I've connected A to all the other cities. How many connections there? How many connections was that? Wait a minute, I'm getting confused. I'm thinking of something else. Yeah, never mind. I'm coming at it a totally wrong way. Sorry. Let's try again. I mean, that was true, but that wasn't helpful. Because that won't tell you all the roads. Let's try again. What if I was going to start at A? Let's start at A. And I'm going to make a circuit, right? Because we're supposed to do circuits. I was thinking of connections instead of circuits. I'm getting my two formulas confused. We're supposed to make a circuit, right? From all those cities. From A, again, it's come on, A, and then B, and then C, and then D, and then E, and then F, and then G. 7, 1, 2, 3, 4, 5, 6, 7. 7 different cities. All right, I'm supposed to, let's just list one. Here we go. A, B, C, D, E, F, G, back to A. So that's one route. That's one loop. It's a Hamilton loop, right? Visits all the cities exactly once, comes back home. Great. How many of those are there? Let's make another one. Instead of A, B, C, I could go A, C, B. And then D, E, F, G, A. That's a second one, huh? That's a little different route. Not much different, but a little different. Remember, you can fly from any city to any city, so that's different, but hardly different. So how many total different routes? 720? There's 720 different routes. Again, where did they come up with that number? Well, now we're in position to do it. Think with me. We're going to start with A, and we're going to end with A, right? You have to start and end at home. Start at A, end at A. Okay. Wait, is that true? No, that's not true. You don't have to start at A, do you? Because they said how many total different routes. That could start at any city, yeah. That could start at any city at all. Well, let me just go back to starting at A. Sorry, I'm not being very clear on this. I'm trying to prove this as we go. So start at A. Once I'm starting at A, next I'm going to write a bunch of letters, cities. How many is there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 in between. And then back home, right? I'm going to visit the other 6 cities and come back home. Good so far? How many choices do I have for what city comes next? Yeah, don't I have 6 choices? Right, because you're at city A. There's 7 total cities, right? 7 total cities. You're at city A. You have to make your first trip. I have 6 choices. Got to go to one of those other 6 cities. Okay? And, like I go to B next or C next or whatever. And then, next, how many choices do I have for where to go next? 5 choices. Right? After you go to A and then some other city, you've got 5 choices. Because there's 5 cities left to visit. And then you've got 4 choices. And then you've got 3 choices. And 2 choices. And when you get to here, you've only got one. There's only one city left to visit. And you multiply these numbers together. Whenever you have choices and options, you multiply them together. Are you aware of that? Like what if you have 2 pair of shoes and 2 hats? How many different outfits? Or let's say you have 3 hats. 2 different pair of shoes and 3 hats. There's 6 different outfits can come out of that, right? You know what I mean? Get the idea of multiplying when you have options. So that's what we're doing here. If there's 6 cities you can visit first, then 5 cities, then 4 cities, then 3, then 2, then 1. If you multiply that together, guess what you're going to get? That's the 720. That's the 720 different circuits that are possible. Does that make sense? Now, you might say, if I was you, I'd be sitting there thinking, no way, Mr. Aaron, but you just started with A and ended A. But what about those that start with B, or start with C, or D, or E, or F, or G? What about the other starting points other than A? Do you realize those are all going to just be repeats of the circuits we've already counted starting and ending at A? Am I giving you too much information in a confusing way? If you start at A and do some loop like this, is it any different if I started at B and did that same loop? That's the same loop, you see. So if you just count all the loops that start at A, you've got all the loops, period. Because you could start any of those loops somewhere else. So this is all the loops, 720. So long story short, whatever this number is, what does that look like? 6 times 5 times 4 times 3 times 2 times 1? What is that? 6 factorial. That's 6 factorial. If they're asking me how many total ways can you visit all the cities when there's 7 cities, the answer is 6 factorial. Everybody tracking with me on that? When there's 7 cities, there's 6 factorial ways, different loops to visit all the cities. So what if they asked me K10? You have 10 cities. Then it's going to be 9 factorial different possible loops to visit all the cities. Get the idea? So if it's Kn, let's write a general formula. N minus 1 factorial. There's the formula for the number of loops possible. Everybody tracking with me? Number of loops, or they call them circuits, whatever, same thing. N minus 1 factorial. See how we figured that out? If you have N cities, there's N minus 1 factorial possible trips visiting all those cities. Possible loops. We just saw the pattern. We just followed the pattern there. Okay. So everybody got that copy down? I'll move on from there if you're good. So think with me for a second. If you have 10 cities, what if you're the FedEx manager and you're looking at a map of 10 cities where you got to deliver a bunch of packages? And you're thinking, all right, I got my plane in one of those cities. He's going to fly and visit all the cities and come back home at the end of the day. Which route should he take to be cheapest, save money? How many different possible trips visiting all 10 cities are there? What are the number of different trips or loops or circuits, whatever you want to call them? How many different possible trips are there? Well, what did we just learn? For 10 cities, there's how many? 9 factorial. Right? It's 9 factorial. We good there? So it's 9 factorial. You guys have your calculator? What is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times, or just hit the 9 factorial button? 362 what? 880. 362,880 different loops, ways of visiting all the cities. Are they drilling out there? What's that? Oh. I usually ask them to do that during a test day. No, I'm kidding. All right, make it a little more challenging. No. 362,880 different loops are possible. So if you're the manager, the FedEx manager, you're looking at 10 cities, 9 factorial, right? Because you're going to start at A, you're going to start where your plane's parked. Then you have 9 cities you could go to next, then 8, then 7, then 6. 9 factorial, 362,000 different ways to do that. You're not going to do this by hand, are you? What are you going to do? Real life. What are they going to do? They're going to have a computer program. They're going to have a computer program where they just say, computer, let's start looking at those 362,000 different loops and tell me the one that's cheapest. And that's what computers do. That's why we love computers, right? They're super fast. Computers actually are not smart. They don't know anything, in fact. They just run numbers super fast. That's all they are. They're lightning fast. So a computer can crank out 362,000 possibilities in probably a minute or maybe 10 seconds even. Crank it out and give you the cheapest route. And then you tell your pilot, fly in this route, visit the cities in this order, save the most money possible. That sounds good. But let's think for a minute about real life. Are there 10 cities, say, in California? Let's just stick to California. We don't go to the whole United States. Just sending packages within California. No, not even close. How many cities are there in California? Well, I don't know. 50 at least. 50 major cities, at least, in California. Right? Okay, so what? Is that a big deal? Yeah, that's a gigantic deal. You guys have your calculator? What's 50? Remember, 50 factorial tells you how many different trips there are among those 50 cities. So what if you're looking at 50 cities? That's more like real life. Right? Your plane is going to visit 50 cities in California. What is 50 factorial, or 49 factorial, whatever? Basically the same thing. What is it? It's crazy big. Yeah. It makes the national debt look like nothing. It's crazy, right? Because your calculator, doesn't it say something like E, or it has a number on the right, like, what is it, 23 or something? Or times 10 to the 64th. Okay. You know what that means on your calculator when you're, well, tell me, what does your calculator say exactly? What does it say? It says 932, and then it has times 10 to the, or E, depending on your calculator, 64. Do you know what that means? What is that 60? And different calculators will show it different ways, but somehow they'll have a 64 on the right. Space in the 64, something like that. What does that 64 mean? Do you know what that means? What does it mean?
To the power of.
To the power of. And what does that mean I do with this number? The decimal doesn't really go here. It goes where? 64 places to the right. 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 places. I've got 56 more zeros coming after that. That number is crazy big. So big that, in fact, computers can't do it. Computers cannot handle it. That's what we're going to see in this very question. They're going to say, okay, suppose you've got the fastest supercomputer in the nation. So what we're going to basically show now is that this is a big problem, and we need computer technology alone can't handle it. We need some good math ideas, because technology alone can't handle it. Suppose you have the fastest supercomputer that can do 1 trillion circuits every second. I mean, that seems pretty quick, right? That's real life. It can look at 1 trillion circuits in 1 second. How long would it take to handle just K24, let alone 50? Just 24 cities, right? K24 is a complete graph, 24 cities. How long would it take? Well, I've already calculated for you, and I'll show you how to do that. The answer is 820 years. That's how long it would take the computer to come up with the answer. I don't think we can wait for that. So this is why we need logical math things to help technology here, because technology alone can't handle this problem. It goes right over the top of technology to see how big the problem is. So how do we come up with that 820? How do you actually calculate? Let me show you how we do that. And you're going to want to write this down, put it in a 3x5 card, because there's likely one of these on the exam. So I want to make sure you feel the weight of this question. This is a big problem. So this is all to show that we need to do it a better way, because this is too hard. So here we go. So they're asking K24, so part A, K24. What do? Well, you know it's 23 factorial, right? Remember, you go one below that, 23 factorial. But that'll be the total number of circuits. I don't care what that number is. I'm not even going to write it down. But then that's the total, again, the total number of circuits, number of different loops, different trips or loops that are possible, right? That's all the different trips that the computer has to look at and figure out which one's best, which one's cheapest. So that's some gigantic number. I'm not even going to write it down. But how do we figure out how long it'll take the computer to do that? Well, first off, you have to divide by 1 trillion, because the computer can do 1 trillion circuits in a second. So if you take that 23 factorial number, whatever it is, and you divide by 1 trillion. Now, what is a trillion? It is 10 to the, what is it? 6 would be 1 million. Yeah, let me give you this information. 10 to the 6 is 1 million, right? Because that's 6 zeros. You guys know that one, huh? 6 zeros, that's 1 million. right? That's a million right there. Good. 10 to the 9th is billion. So billion. And then 10 to the 12th is trillion. And they're not going to ask you any more than that. So basically, they ask you million, billion, or trillion. There we go. So let's put it in there. So divide by, so I'm going to divide by 1 trillion. Shouldn't have erased that, which is what? 10 to the 12th power. You guys know how to do the powers on your calculator? I'll be glad to help. Let's do that. 10, there's two different power buttons. It's like up arrow or it's like X to the Y. It depends on your calculator. 12. So 23 divided by 10 to the 12th. See what we're doing there? Because that's a trillion, right? Remember, the computer can do a trillion circuits in a second. So if this is the total number of circuits it needs to look at, and it can do 1 trillion every second, then if you divide this, you'll find out how many seconds it's going to take. Because every second, a trillion circuits, trillion circuits, trillion circuits, trillion circuits, right? So if you divide by a trillion, you're going to get how many seconds it would take. But we don't want to stop with seconds because they asked us years. So right now we're in seconds. How do you convert seconds to years? Well, how many seconds in a minute? 60. So we divide by 60. Now we're in minutes. How many minutes in an hour? 60. Now we're in hours. How many hours in a day? Now we're in days. How many days in a year? 365, unless it's leap year, but we'll just ignore that. There's what you do. So you're going to want to write that down in your 3 by 5 card. So it's 23 factorial divided by 10 to the 12th, divided by 60, divided by 60, divided by 24, divided by 365. That takes it from seconds to years. And you should get the answer rounded, 820 years. So you guys have your calculator? Let's take a minute. I want to bounce around and help you.